Hello again. So for the rest of week 8 here, we're going to finish off chapter 6, dealing with normally distributed data and sampling distribution some more. And this section talks about assessing normality. And so many of the things we've done so far require that a data set be normally distributed or approximately normally distributed. So to figure that out, we need to first of all define what does it mean to be normally distributed. Well, that means to have that bell-shaped curve. And two of the functions we use for that, we can construct a histogram and see if that histogram is approximately bell-shaped. If it's symmetrical or approximately symmetrical, we're good. But if it's extremely skewed in either direction or if there's major outliers, that tells us that we don't have to go any further. It's most likely not normally distributed. And second, there's something called the normal quantile plot. Now, you can do this in Excel, but it requires an add-in. And I try to avoid having you do excessive add-ins in Excel. So I will show you how to do it without the add-in, just to analyze a set of data. The normal quantile plot is just a way of graphing the data values on an XY scatter plot, where X is the data value and Y is a normalized value that we calculate from the normal distribution. So again, the two tools we're going to use are the histogram. First of all, if you do the histogram and it's overly skewed, I wouldn't even bother with a normal quantile plot. Some people say that the histogram is enough, but it can miss some things. In most applications, though, just the histogram is an adequate assessment. Also, you can do box and whisker plots and other plots that can be used as well to give you a decent idea if a data set is approximately normally distributed. So if it is a normal distribution, the data points will form that kind of a bell curve. It'll be symmetrical on the histogram. On the normal quantile plot, they should form a straight line. So if they don't form a straight line, then you have to look at what they are. If they're randomly kind of spaced around the line, it might still be approximately normally distributed. If it forms a pattern, though, then it's not normally distributed. If it's a systematic pattern around that line, then it would definitely not be normally distributed. There are more advanced methods like the Ryan-Joyner or Shapiro-Wilk test, and several others you can see listed there. We're not going to get into those for this course. So like this picture here, you can see on the histogram, switch colors here, that this is very, very slightly skewed to the right side. On the normal quantile plot, you can see those data points are really close to being on the line. Now you might look at it. I don't see a very definite pattern. You might say, well, there's a slight curve like this. But I would say there's not a definite enough pattern there that you would want to disqualify this as being approximately normally distributed. I would say this is pretty close to being normally distributed. This, by the way, is representing IQ scores. This one here, however, is actually uniform. You can see the histogram is a rectangle. There is no curve in the top at all. So just looking at this, I would say, I would see the histogram and say there's no use even doing the normal quantile plot because this is not normally distributed. I would stop right here. If you do the normal quantile plot, you can see it's kind of subtle. At first glance, the points, they're pretty close to a straight line, but you can see there's a definite pattern. They make an S curve above and then below the line like that. So there is a definite pattern there. This is not a approximately normally distributed set of data. Here we have a skewed set. Now this is extremely skewed, extremely stretched out in that right direction. I wouldn't even bother with the normal quantile plot. You can see here we don't even come close to being on the line, much less worrying about forming a pattern around the line. So if I want to construct the normal quantile plot by hand rather than using an add-in in Excel, how do we do that? Well, I'm going to go ahead and give you an example of that right now. So here's my data set right here. Oops. Column B, I have 10 numbers there. I have numbered them, labeled my I value here, 1 through 10. Now for each of them, I'm going to calculate an AI value. AI is equal to 2i minus 1 over 2n. So n here is 10. There's 10 numbers in the list. These are my I values. So AI, it's going to equal, parentheses, 2 times this value. Oops. Minus 1 divided by 2 times n, which is 10. So I get my AI values. Now these should be evenly spread out between 0 and 1. And you can see they are. And then I want to calculate something called a ZI value, which is the inverse normal. It gives me the probability of being less than this value. So this is going to be, actually the z-score that has a probability of this being less than it. So your normal inverse is what I want here. This probability for a mean of 0, standard deviation of 1. And it gives me a z-score that corresponds to a left tail probability of AI. And again, you'll see that's symmetrical. So what I want to plot here are these values. So I'm just going to copy these and bring them over here. And I'm going to copy these. Then I'm going to do a paste special here, so I just get the values. And I'm going to graph these two in a scatter plot. There we go. And you can see these points, those are relatively close to a line. If I wanted to draw a line through them, I could. And you can see they're pretty darn close. I mean, you might think they're a little bit below here and above there, but I don't see a huge definite pattern there. This is pretty darn close to being normally distributed. So I would say this data set is approximately normally distributed because those points are really close to being on a line. And that is assessing normality. The final section then of Chapter 6 talks about using normal probabilities to approximate binomial probabilities. This used to be a very common thing because the formula for binomial probabilities is a very complex formula. You recall that it was, probability of equaling x was n choose x times p to the power of x times q to the power of n minus x. That n choose x is the factorials. Remember, that can get complicated just in itself if the numbers are large. Big numbers to calculate here, and it all divides out to be something between 0 and 1. When back before calculators and technology, when that had to be done by hand, it was a complex calculation. Well, normal probabilities, we had the normal probability tables already figured out, so we could use those tables. So those big probabilities, when n was large, it was easier to convert it into a normal probability. So the key concept here, remember when we're dealing with a binomial distribution, the mean of the binomial distribution is just n times p, where n is the number of trials and p is the probability of success on each trial. And the standard deviation is the square root of n times p times q, where remember q is just equal to 1 minus p. It's the complement of p, or it's the probability of failure. The condition that had to be met is we had to reasonably expect at least 5 successes and 5 failures. So we had to have a large enough sample size, a large enough number of trials to expect at least 5 successes and 5 failures. This generally is not an issue if We have a probability of success that's towards the middle, 0.5 or close to that. It's when we get really small or really large probability of success. If P equals 0.01, well, now you have to have at least 500 trials to get at least 5 successes. Or on the other side, if P is like 0.98, you'd have to have at least 250 trials to guarantee to reasonably expect at least 5 failures. So that's where that condition comes in, is if you have a really small p or a really large p-value. Remember that the binomial distribution is discrete. So that meant the probability of being equal to a number actually had probability. Whereas normal probability is continuous. And in a continuous probability distribution, the probability of being equal to a single value is 0. There isn't one. Because remember, there's an infinite number of values. If it was greater than 0, we'd have a larger than 1 total probability. Because of that, we have to convert individual values from the binomial or discrete distribution into a range. And we do that by going 0.5 below the value to 0.5 above the value for the range that we're going to look at in the binomial or in the normal approximation. A little bit of a review of the binomial distribution. First of all, we have a fixed number of trials. That was X. The trials are independent, which means the result of one trial does not affect the probability of the next. The results of the 2 trials can be classified in 2 categories of success or failure. And finally, the probability of success stays constant from one trial to the next throughout the whole experiment. N was the number of fixed trials. X was the number of successes out of those N trials. P is the probability of success on any one trial. And Q is the probability of failure. Remember, Q is 1 minus P. The rationale, we don't need to get into proving why this works. We'll look at an example of that calculation in a little while, though. So again, to review, we must have reasonably expect at least 5 successes and 5 failures for this to work. And we need to know N and P so that we can find the mean and standard deviation of our distribution using these formulas again. And so we are going to use the normal probability given that mean and that standard deviation, and of course the continuity correction, going from 0.5 below to 0.5 above to get a single value. So I'm going to do a couple of examples here. Now let's look at the procedure here first. So one procedure, make sure you check the requirements. Make sure you've got that reasonable expectation of at least 5 successes and 5 failures. Find the mean and the standard deviation for the binomial distribution. Remember to apply the continuity correction and then calculate those probabilities. So I'm going to do some examples here. I'm going to insert a blank slide quick. Maybe. And so first one I'm going to look at is a small example. But let's say out of 120 students. Well, let's do this. 78% of students pass statistics. On the first try. Out of 120 students, find the probability that one exactly 85 pass. So for binomial, this would be the probability that x equals 85. For normal approximation, this is going to be the probability that 84.5 is less than x is less than 85.5. Remember, we have to have that range. So now in Excel, let's just do some calculations here. Let's do the binomial. Then over here, we'll do the normal approximation. So in the binomial, it's going to equal binom dist. Our number of successes, 85 out of 120 with a 0.78, because 78%, and no, not cumulative. For binomial, we have to, or for the normal approximation, we have to do two calculations here. So we have to do 85.5, the larger number. The mean has to be calculated, so I've got to come back and do this quick. Let's find our mean here. Which is going to equal the 120 times 0.78. And we're going to find our standard deviation, which is going to equal the square root of 120 times 0.78 times 0.22. That's 1 minus the 0.78. Giving us the 4.5378. So this is going to equal normal distribution. Remember, for a range, we have to subtract. So we're going to do the larger one, 85.5, with a mean of 93.6, standard deviation of 4.5378. And yes, it's always cumulative here, minus the normal dist of 84.5 for 93.6. 4.5378, and cumulative. Notice we get a really close to the same number, 0.0149 to 0.0147. So really close to the same probability for that example. What if I ask less than 100 pass? So for the binomial, this is just probability of x less than 100. Notice it's not less than or equal to, because I didn't say no more than 100 pass. I said less than 100 pass. So when we convert this over to normal for a continuity correction, we've got to make sure we don't include 100. So we're actually less than 99.5 for the binomial, or for the normal approximation. So in the binomial, binom dist, 100 out of 120.78. And this one will be cumulative. This one will be normal dist, 99.5, comma, oops. This one should not have been 100. I have to go back and change that one. Just a second. 93.6, 4.5378, and cumulative. This should have been 99, because remember, we're not including 100. And there we get 0.9061 to 0.9032. Again, pretty darn close to the same value. So the reason I had to change that to 99 is this here, to enter it into Excel, Excel only accepts it in the form of being less than or equal to. So that's the probability that x is less than or equal to 99, because the 100 is not included in that. The example the textbook wants to use here is talking about Mendel's experiments with peas. His genetic experiments, he predicted 25% would be yellow. So out of 580, that would have been 145. But he actually got 152 yellow peas. So is that show that is that significantly high based on Mendel's assumption that 25% should be yellow. So if we take a look at this, if we're looking binomial, this is what's the probability of x being greater than or equal to 152. By normal approximation, it would be the probability that x is greater than 151.5, because we are including the 152 in here. We have a mean. If we use our binomial formulas here to get a mean of 145 and a standard deviation of 10.4283, let's find those probabilities. So I'm going to do it in Excel here. So the binomial distribution probability, 152, 145, 10 point, just got to glance at that, 4283. And we do want to go cumulative, but we wanted greater than. This is going to give us less than. So I'm going to go back here and slip in 1 minus to get the, oops. Oh, what's wrong there? Number of successes, 152. Number of trials, 580. I entered that totally wrong. So we had 152 successes out of 580 trials. Probability of success, we're assuming 0.25. And yes, I do want to go back and make that 1 minus. So I'll enter that correctly. I was thinking of what I wanted to enter for the normal approximation there. So this will equal normal distribution. Now again, this actually should be 1 minus because we want to go greater than. And so we want to be 151.5. For that continuity correction, a mean of 145 and 10 point, got to look at that again, 4283. And cumulative, of course. And you can see there we get really close to the same probability. This is a 0.2348. This is a 0.2665. Basically right around 25% chance. So the question is that unusual? Does that mean he is wrong? So we use those probabilities. Let's get down to the actual calculation here. We get the 0.2665 just like we found. Because this is not terrible, 25% is not significantly low or anything like that. So we would say this is still acceptable. This could still just be the result of random variations. Genetics is not a definite to the numbers science. It predicts probabilities, but it does not predict absolute numbers. So if the rate of yellow peas is truly 25%, getting 152 yellow peas out of 580 is not a significantly high value, so it does not contradict Mendel's theory. And that's really all we really want to do with that. I don't want to get into a lot more examples. So that wraps up week 8 here with our chapter 6. Next week, we're going to get into the actual more inferential statistics of actually starting to draw some conclusions about our population parameters.